Welcome. In this lesson, we're going to have a look at some practical examples of exponential functions. Now, we've already established an exponential function is something that has a variable power, something that might look like this: y equals 2 to the x, looks about like this, where it's got an asymptote at the x-axis, where it's got a y-intercept of 1, and as x gets big, y gets really big, and as x becomes negative, y becomes really small. Or we could have a look at something where we might have a negative involved, maybe something like y equals 2 to the negative x. Doesn't have to be 2, by the way. I've just chosen ones that are similar to each other. 2 to the negative x, where we end up with actually a reflection, because then now when x becomes negative, y actually becomes really big, because we've got a double negative situation happening in that power, and the reverse is true when x becomes really big and positive. We can do things like if we had one that we wanted to look like this, that would be something like y equals negative 2 to the x. So that's a few basic things there. Now, some examples of practicalities of exponential functions. You already know a little bit about this. You just don't know that you know it. So one really simple example is the future value formula. Fe equals PV 1 plus R to the n. This n up here means that we've got an exponential function. Okay, so if I told you I'm investing $500 and I'm going to invest it at 4% per annum, I'm going to call that, in fact, rather than 4%, I'm going to call it 0.04. So that means I've got 1.04 to the power of n for how many years I invest. Well, I've got an exponential function because I've got a power that I can change. I could make that 1 year, 2 years, 3 years, 5 years, 15 years, and that's my variable power. Okay, my power can change, which means that I have an exponential function. So something like that when we graph it. Now the difference here with the future value question is we never have n being negative. So this left part of the graph here, if we were to think about graphing this, we were to do something like this, that would be what our graph would look like. It would look like an exponential. The scale would definitely be different. It wouldn't have a y-intercept of 1, it'd have a y-intercept here of 500, because that's where I start my investment. But in fact, what would happen is all these values here would just go, and in fact this could go as well, because we never get to a negative amount of money, and we just look at that part of the graph. This part here, it's part of the exponential, but it just can't exist because our amount of time can't be negative. Our n number of periods for investment can't be negative. The same is true if we looked at the depreciation formula or the salvage value formula. Our salvage value is V equals V naught, which is our starting value, 1 minus R to the power of n. And again, if I said to you, well, I'm going to tell you my item started off at $5,000, it's going to lose 10% per annum. I knew those two things. I'd end up with something like S equals 5,000, 0.9 being 90% remaining, or if I lose 10% per year, to the power of n. Now this time when I graph that, we're going to end up with an exponential that's actually going down. Our value is getting very close to 0, rather than getting really big as time goes on. It's going in the other direction, but it's never going to become negative. If we think about it practically, our item is never worth nothing or a negative amount. If we think about it in terms of an exponential, we're talking becomes an asymptote, which means it's never going to hit that line. Let's have a look at a couple more examples. An example here about the number of germs in a particular culture. N equals 1,000. That's out of 6.9 to the power of t. T being our time in minutes since we started measuring the number of bacteria. And we're going to see how this grows as time goes on. One of the key features with an exponential is something is growing according to itself. So if we think about money, if you have more money, you gain more interest, which means it grows quicker. If we have more bacteria in a culture and they divide by mitosis, then we end up with more bacteria. So they're growing more quickly, and that's what happens as time goes on, which is why as our population gets bigger, a number of germs gets bigger, it actually grows a lot quicker as well. It doesn't just, there's not just more of them, they're growing more quickly as well. So we've got a couple of things to do here. Calculate the number of germ cells in the culture after 10 minutes and 1 hour. So first thing to do here is find n of 1,000, 6.9 to the power of 10. We're asked to answer here in scientific notation, correct the two significant figures. Putting that in our calculator, we end up with 2.4 times 10 to the 11. Our second option there is n equals 1,000, 6.9, not to the power of 1, but to the power of 60, because we're talking in minutes. This time we end up with 2.1 times 10 to the power of 53. So our first answer there is we've got somewhere in the vicinity of 10 to the 11, which is a little bit more than a billion, getting close to a trillion bacteria or germs. This time, with our second example, we've got 10 to the power of 53, which is something like a trillion. I can't even count that high. Let's continue on here. What was the initial number of germ cells? Initial means when we started, which is when t equals 0. So this is A. We've got when t equals 0. So we've got n equals 1,000, 6.9 to the power of 0. Well, anything to the power of 0 is 1. We can put that in our calculator, or we can just say we started off with 1,000 germ cells. Now, the other thing to note here is if we start off with no germ cells can't come from nowhere. They can't just magically appear. So they grow according to themselves, and if they split and grow according to themselves, there needs to be some of them to start with. If we had 0 at the front here, if we changed that 1,000 and made that 0, well, then the number of germs would always be 0, no matter how rapidly they're growing or how long we left them be, there would always be 0 of them. That's just a little something to note. And the third thing here is estimate when the number of germ cells will pass 2 million. We're asked to estimate because to do that exact calculation, we would need something called logarithms. We don't use these in the standard course, so we need to do an estimation. Now we've got an estimate here. If we think about the first thing we did, which was substitute in using 10 minutes. Well, at 10 minutes, we're well past 2 million. We're up to nearly 2 trillion. So let's see what we could do. Let's pick some numbers here. If I pick t equals, say, let's pick 6. It's just a little bit smaller, and that gives me somewhere in the vicinity of 1.1 times 10 to the power of 8, which is still far too big. So if we pick t equals 4, I'm just picking numbers that make this smaller, by the way. If you went and said, I want to pick t equals 5 and try there, that's fine. Or start at you could just start at t equals 1 and go up from there until you pass 2 million. That could be a valid way to do it as well. I'm just working backwards from the 10 that we started with. And there I end up with 2.2 or 2.3 times 10 to the 6, which is 2.3 million. I'm just a little bit over 2 million. I actually went and checked t equals 3, and that gives me about 300,000. So t equals 4 is the first minute that I have passed 2 million. So that's when I will surpass 2 million there. Only way we can do that is by guess and check, but you can do guess and check in a few different ways. But it is an estimate using approximately t equals 4 minutes. If that was an exam question, it would probably be asked to the nearest whole minute, because I could get closer, right? I could say 3 minutes and 50 seconds or 3 minutes and 55 seconds. But if there is an exam question, it would probably be clarified to give to the nearest whole minute, as I've done here, which is 4 minutes. Last question I want to have a look at here is about a bushfire spreading through a forest. We've got an exponential model here. A equals 5 outside of 1.22 to the power of h, where h is the number of hours and A is the area that is burnt. So what is the initial area burnt? Well, if we're thinking initial is our word meaning at the start. So that means T equals 0 and A equals 5 outside of 1.22 to 0. Now, anything to the power of 0 is 1. That doesn't mean the whole answer will be 1. It, in fact, means the area to start with is 5 hectares, HA being hectares, the shorthand for hectares. Moving on to part B there. What area to the nearest hectare was burnt after 3.5 hours? We're substituting in A equals 5 outside of 1.22 to the power of 3.5, which is 10.02, 10.028 or 10.03 hectares, corrected 2 decimal places there. So you can see in the first 3.5 hours we've doubled. Now the thing about an exponential is it won't take 3.5 hours to double again. It's going to grow more quickly because there's more, if you think about it as in terms of a fire, there's more land burning, so there's more land that's nearby that can start burning as a result of that. So not only does more land burn, it actually burns more quickly as well. Part C is an approximation question. After how many hours will 20 hectares of land be burnt? We need to do our guess and check here. So we've got 3.5 hours. We're asked in hours as well, so I'm happy to go with the nearest whole number of hours here. Let's go and try H equals 5. And that gives me A equals approximately 13.5. We're not there yet. Let's go try H equals 7. If we do that, we get A equals 20.11 hectares. Which is our first time there. If we do go back and check H equals 6, we would just be a little bit smaller than that. So H equals 7 hours. It takes 7 hours for 20 hectares to be burnt. And now we're going to graph this function from 0 to 6. Got a table of values here that I've drawn. I've rounded all of these to 1 decimal place. We found some of these in the previous parts of the question as well, which is helpful. And actually what I did with my calculator is you can take each of your previous answers and multiply it by 1.22, this number here, and that can give you the next answer. So for example, if you take this 7.4, the unrounded version of 7.4, and multiply it by 1.22, that will give you the 9.1, and then the 9.1 will give you the 11.1 if you multiply it by 1.22, and so on. Or you can just go substitute it straight into this equation here. Either way is just fine. So if we go and plot those points, we end up with something approximately like that. It should definitely be a curve. This is not the most rapidly increasing exponential because that 1.22 is quite a small number, but it still should be a curve. If yours kind of looks like a straight line, maybe have a look at your scale or how accurately you've drawn that as well. I haven't been perfectly to scale here, but it is a sketch. If you were to do this in the exam, you would probably be given a grid paper just because of the amount of time that it takes to draw this freehand. So I'm going to plot my exponential in there. I can extend it beyond here, but what we'll notice is one of the last parts of the question is in fact, what are the limits to this model? And so part of the limits to this model is there's only so much land that can burn. So we can't just say this fire will continue to burn infinitely. Eventually it will go out. Let's have a look at the last couple of parts of the question. So we've just done part D there. Use your graph to determine after how many hours 10 hectares of land will be burnt. Well, we can do this using our graph, or we can do this by doing an approximation. Again, after how many hours will 10 hectares of land be burnt? Well, we want to go and find where A equals 10. Looking at our table of values there, well, that the first value that passes 10 for our area is H equals 4 hours. And looking at the second here, the area burnt after 5.5 hours. Well, we could use our graph to approximate that, or and it would be somewhere between our values for 5 and for 6 hours. I'm actually going to go and say if H for part 2 there, if H equals 5.5, we can go and say A equals 14.9 hectares of land that has burnt. So we could do that using a graph if we were really, really accurate, or we can do it using a substitution here. Part F here has got something to do with the fact that this is a real life question, and normally real life questions have a limitation to them. This fire cannot continue to burn infinitely. So you could make comment here. I would be really specific about something mathematical. Okay, I would say the could make lots of other claims getting into physical properties of the land. You could say, well, winter's coming and therefore it's going to get cooler and the fire will stop burning, or oh, it's supposed to rain next week, or we've got amazing firefighters and they'll put out the fire. Yeah, those things are all may be true, but we're talking mathematically here, and anything like this will have a limit to it because something cannot typically continue on infinitely. Just like we started this video talking about money, well, if we invest money for 5 years, 10 years, 100 years, we're not going to invest money for 10 million years. That's just not a realistic idea. So normally practical models do have some sort of limitation, normally where they start and where they finish as well. Our starting limitation here is that h has to be starting at 0. H is never negative. And our end limitation is, well, we don't know. How many hours is it going to be? 10 hours, 100 hours? We don't know exactly where that endpoint will be, but H will not be 10 million hours because that's just not a realistic number to deal with. I hope this has been helpful.